We all use pencils, but what are pencils actually made of? What is it that makes us able to write with them and have dark marks appear on paper? How did we get to this point? In the case of the modern pencil, they are made by inserting shafts of graphite into wood. But what is graphite? Graphite was first discovered by villagers residing near Greynotts Hill in England. This was about 1565, but it wasn't until 1779 that Swedish scientist Carl Scheele discovered that graphite was actually a form of carbon. Scheele had been inspired by the experiments performed by Joseph Black, Joseph Priestley, Antoine Lavoisier, Pierre Macquer, and Louis Claude. During the 1700s, these scientists attempted to intensely heat various metals and minerals and observe the gas released, either in a sealed jar or forced into water. Interestingly, this is actually how we discovered soda water. But it was these same set of experiments that concluded that diamond, chalk, and charcoal are all composed entirely of carbon. Scheele's new information only added to carbon's growing reputation of forms. But what gives carbon its ability to appear in so many varied forms? Modern research has not only yielded more carbon discoveries, but allowed us to see that the variance is caused by structure. While diamond exhibits carbon atoms arranged in a three-dimensional form, graphite appears as layers of two-dimensional sheets. This inconsistency is largely due to their varied electron configuration. Carbon only has 4 valence electrons, thus allowing it to make many bonds, sometimes even with itself. We would expect carbon's electrons to take up space in the 1s, 2s, 2px, and 2py orbitals. Within the second quantum principle, the 2s orbital has 2 electrons, while 2px and 2py each only get 1. This distribution of carbon's 4 valence electrons is due to Hund's rule, or the empty bus seat rule, that requires each orbital within a shape group to have 1 electron before doubling up. In the case of graphite, however, carbon's electron configuration is hybridized to an sp2 form. This means that while the 1s orbital remains the same, both 2s orbitals and one of the 2p orbitals combine to make 3 sp2 orbitals. These orbitals appear as half a dumbbell with a node on the other side, the hybridized form of the s and the p orbital. But wait, you think, sp2 hybridization has only accounted for 3 of carbon's 4 total valence electrons. Where did the 4th go? Well, the remaining electron is given to a regular, non-hybridized p orbital that will later serve to form pi bonds. On the left side, this diagram shows 2 sp2 hybridized molecules. Each has volunteered 1 hybridized orbital, pictured in red, to covalently bond with each other and form a sigma bond. On the right side, the regular p orbitals, shown in gray, come together on top of the sigma bond to form an overall stronger pi bond. This is commonly referred to as a double bond. Since the pi bond goes on top of one of the already existing sigma bonds, the overall structure for sp2 is still two-dimensional. We call this trigonal planar. Though the electrons' negative qualities typically repel each other as much as possible to form 120-degree bond angles, the double bond provides more negative force, and thus the other 2 orbitals are repelled further from the pi bond closer to each other, creating a 116-degree bond angle between the 2 of them. For functionality, however, this is often just rounded, as is seen in this diagram of graphite, where sp2 hybridized carbons endlessly form bonds with one another to create these graphite sheets. In the grander scheme of things, the random distribution of pi bonds supports graphite's conductivity properties. The sheets of graphite are only held together by intermolecular forces. This attraction is caused by momentary dipole-forming electron imbalances, and the connection is much weaker than a regular bond. So if graphite is made of carbon, why doesn't the diamond look like graphite? Carbon appears in other forms because it has the ability to form a different electron configuration with itself. In the case of diamond, its sp3 electron configuration allows it to have an overall 3-dimensional structure. Collectively, these are called allotropes and include not only diamonds and graphite, but soot, charcoal, and fullerenes. Fullerenes are a large family of carbon structures commonly recognized as buckyballs. So there you have it. Carbon, the same element in your pencil that's also found in your diamond ring, your fireplace, and your toys.